This is part one of the event recap of this week. I'm going to talk about one presentation in this first part, and that is going to be Tierry Tambo. He is a hardware specialist. His work is kind of along the lines of Onur Mutlu, which is how can we design efficient hardware for current machine learning loads. What I like about Thierry's presentation is that he's very structured and very intuitive about his approach. I read his dissertation, and in that dissertation, you can see the approach already. It's a very sort of fine-grained, but high level, and then very detailed, technical at the same time. So pretty intuitive. Now, his statement is, my research is building a heterogeneity of solutions co-optimized across the algorithm, the memory system, the hardware architecture, and the silicon. So what he's really doing is going across the stack, trying to find optimizations. And what I find most interesting is he's focusing on transformer architectures. So there's a couple of things that he tackles that are interesting from a technical perspective, but also sort of from a big picture level perspective. If you think about, let's say, how do companies like NVIDIA optimize for workloads? How do they achieve improvements? For example, NVIDIA recently at the Hot Chip conference, the chief science officer actually spoke about this, how they can improve better than Moore's law because, for example, of sparsity. So Thierry talks about that. And he talks about eDRAM, for example, which is embedded DRAM for embedded devices, how to do training and inference on the device by using a different type of memory. He's talking about sparsity, of course, numerical analysis of precision, and how you can generate more precision with maybe less power. He's talking about entropy encoding and early exit. So this is the idea here is that if you have a deep neural net, so you could maybe spare yourself some of the layers and just exit the training, either because you already think you have the result or because you think you need more resources. You can have adaptive voltage, which is the technical term for that would be, let me just get there. The technical term would be dynamic voltage frequency scaling. So you have, based on the workload, different types of frequencies and voltages. So those are the kinds of things he's talking about. And I think the purpose of this podcast is to give people a sense for what it feels like to run a hedge fund. So why am I talking about the dissertation of an electrical engineer who is going to be professor soon here at Stanford? And the reason is because it's a very nice example of what kind of technical challenges and what kind of approaches can be used to solve problems and generate products and services that can help solve those problems, in particular, let's say in this case, generative AI. And I think this is really important for investors, for employees, for people who are in the field to understand, okay, where are the pain points and how can we tackle them? This is not even on podcast. It's December 1st, 2023. This is Krimdelko. Since the last update, we're down 5.3%. The market is up 1% for the year. We are up 107.9. The market is up 19.6%. We're outperforming by 87.3%. Before I go into the discussion of Thierry's presentation, just real quick about the Cybertruk launch, which happened yesterday. So Cybertruk was launched, and I think the biggest takeaway, of course, is pricing and specs, and there's a bit of disappointment there now. I think the Cybertruk still has all the potential to become the most important hardware product since the iPhone launch. That's my interpretation of it, because it's a lifestyle design and technological sort of breakthrough, and therefore we believe that although the pricing is a little bit on the steep side and the performance metrics may be a little bit lower than we thought, it's unfortunate that that is the case. I think it was expected because of the delay. So 4680 is not ready, and then of course pricing is high because of low volume. Hopefully we'll get there, and that remains to be seen now. But we believe that nevertheless, the Cybertruk launch is a big event for Tesla and a good event, and it should proliferate this product and the whole technological architecture that comes with it going into the future. And this is a nice segue into Thierry's presentation. Before I go to Thierry, I just want to say what's important about the Cybertruk launch is not just, of course, the truck and the product and the margins that you can get on that and all that stuff. Okay, what's really important here is that this is a new technological platform. We have single casting, we have 48-volt architecture, we have massive weight with massive performance. So a lot of these kinds of things that are very difficult to achieve have been achieved, and we're of course at the beginning here, but it's an engineering optimization problem that can be fine-tuned, that can be improved, and that's really what engineering is all about. And I think that's what Tesla is all about, and that's what we're investing in at Orange Capital Partners. Now let's talk about Thierry's presentation. I think it's a fantastic presentation because it really encompasses everything that engineering is about, everything that engineering, technology, and wealth creation is about. That, at least that's the way we see it, because it's really tackling problems at the core, finding solutions. And since we're talking about big impact, remember the purpose of Orange Capital Partners is to invest in wealth creating strategies. The actual mission statement is we invest in fundamentally new concepts and engineering practices with large impact. This is what we do. This is disruption in a nutshell. And what Thierry is presenting is maybe not disruption in a sort of the sense like the iPhone or the Cybertruk or SpaceX or something along those lines. It's an improvement. It's maybe, you could even say it's incremental, but it's not just that. I think it's more than that, because he's suggesting solutions to real problems that are right now in the space for machine learning, in particular deep neural networks. He's suggesting real solutions for transformer technologies, and I spoke with him after the presentation. This could be a gateway towards multimodal transformers, in other words, robots and things along those lines. And then we could see real disruption. And this is a nice example of how engineering and ingenuity and creativity and technical know-how can lead to massive improvements in maybe adjacent technologies that can then become very disruptive. So now what am I talking about here? The fundamental problem that Thierry is tackling is that Dennard scaling is coming to an end. Dennard scaling is sort of a cousin of Moore's law. Dennard scaling is sort of, the idea was that with more reduction in area of chips, we have constant voltage and frequencies, and therefore we can scale down without using the relationship between area and voltage and frequencies is constant. So the less area, the less voltage and frequency. That was sort of the Dennard scaling idea, and it is unfortunately not happening anymore. So in other words, now you have actually an exponential increase in the voltage per whatever square micrometer and stuff like that. So what that means is the end of Dennard scaling means we need to find solutions for two fundamental problems in hardware design for machine learning workloads. One is power consumption, and the other is memory. They're both related. So what I mean with that is most of the power consumption now goes into the transfer of data from memory into the compute, into the ALU, the arithmetic unit, and that can be solved in different ways. One way is to have memory on chips, so SRAM, for example, and that's already the first solution that Thierry offers, which I think is really interesting. It's called eDRAM, so embedded DRAM for edge devices. And the idea here is that you have a storage on chip, which requires less transistors, has the requirement of more frequent refreshes, so it does the data doesn't stay as long, but because you're doing it for machine learning workloads, you can, and machine learning workloads have a lot of transient data, in other words, weights that are being updated constantly. So you could potentially design an algorithm that updates the weights faster than the refresh necessity, and therefore you could still use a DRAM that is maybe not as stable like SRAM, but still does the job. So to me, this is a beautiful example of ingenuity, of creativity, and it shows how engineering solutions can really help. Another one that he talks about a lot is sparsity, and this is something that NVIDIA spoke about at the Hot Chip conference. The chief science officer at NVIDIA, he actually mentioned him in the presentation. Now, sparsity, the idea of sparsity in simple terms is if you have zeros, you don't need to store them, you don't need to compute them, you don't need to move them around from memory into the compute unit. In other words, you can disregard zeros. And how do you do that? And he shows really nicely in his dissertation how different types of algorithms, for example, RNNs, DNNs, convolutional neural nets, and then transformer architectures, how they have different types of distributions of weights. What that means is that when you have a very narrow histogram of weights, you can quantize easier. In other words, you either have a weight which is, let's say, between 0.4 or 0.7, or you have nothing, or you have a 1 or a 0, something like that. In transformer technology, the weights are a lot more dispersed, and that means that you can have weights like 2.5 and then weights minus 10. Like, it's a lot more wide, and therefore you have more trouble of quantization. And that means that you need to find ways to do sparsity in a more intelligent way. And Thierry offers solutions here. His actual solution is called adaptive float. It's like the name says, it's more flexible. It adapts to the workload. It adapts to the data. It looks at what is coming and then truncates, quantizes the data accordingly. So this, to me, is another beautiful solution to a problem that is out there, and this is something that he's applying at NVIDIA. Adaptive attention is another solution here to deal with transformers in particular, and I find that really fascinating. So you have the attention mechanism, which is, the way I understand it, it's kind of like the context window. Imagine you could have a flexible context window in transformer architectures. And therefore, if you have a prompt that requires a large context window, you use a large context window. If you have a prompt that requires a low, you use a low one. Again, this is adaptation, flexibility, key. And another thing that he mentioned is entropy exit and DVFS, which is dynamic voltage frequency scaling. That is the idea here is the following. Now, entropy exit and dynamic voltage frequency scaling are sort of related. Entropy exit is, think about it this way. You have a prompt that requires a lot of, that is very complex. A very complex prompt will require the network to go through all the layers to find, or two more layers to find a appropriate activation. A less complex prompt will not require that, so you can cut it short. Or in another scenario, you can actually do the opposite. If you think that the prompt is too complex for the amount of, let's say, voltage that you're applying, or the amount of compute resources, or the model that you're using, maybe you should send that prompt to a much deeper model with more layers, so you can have more flexibility in training. So you have flexible models, flexible adaptation of training based on inference. In this case, okay, if the prompt comes, it's of course inference, but you can do the same thing in training. You could think of, like, if let's say the training data shows a lot more entropy than maybe your current model can take, you apply a different model. But let's stay with inference here. The idea of inference is that you have limited resources to do inference, so you adjust the amount of compute that you do based on the prompt. So this is flexible inference, flexible compute, and you can do that with entropy exit, so EE, and then the dynamic voltage frequency scaling. That is, the idea there is that's an old idea according to Thierry, reading his paper and his dissertation. That's an old idea, but it can be fine-grained layer by layer. This is the key. Layer by layer means you don't just do coarse DVFS, you do it layer by layer, and you can save energy again on a layer level. So to summarize this last idea, this entropy and DVFS, one of them is you can maybe spare yourself the layers. The other is you can at least optimize layer by layer how much frequency and voltage you need. The last thing I want to say is, again, one of the advantages of a sabbatical that I'm doing here at Stanford is sort of the cross-pollination and the ideas that I get in different fields and different different topics and all that stuff. And yesterday I attended a lecture about Andrew Sachs. He gave a lecture about the idea of, well, why do we even have deep networks? What's the purpose of depth? And today I have Thierry's presentation about how to optimize for depth. So these are two related concepts that, in my opinion, are a lot more important. There's a lot more depth here, pun not intended, than one might think. Then in Andrew's presentation, the question of depth was about the learning efficiency. How fast do we learn, and do we have these local minima where we can plateau and then get to faster? Maybe if we use less layers, we can get faster learning. But then in Andrew's dissertation, clearly the idea of deep nets comes from the idea that we can have simple representations layer by layer that then add up to very complex results and activations. Now, in Thierry's presentation, we take that as a given. So we want to have deep nets. We think it's a good idea, but how can we optimize them? And we can optimize them by having dynamic frequency dynamic voltage frequency scaling, which is, again, the idea that we adjust the voltage and the frequencies applied layer by layer. And early exit is we adjust we prune the depth of the network based on the complexity of the data that comes in. So those are the ideas. To summarize Thierry's presentation, it's a beautiful example of how we can, how engineering works in a nutshell. I mean, this is engineering at its best. This is engineering at a level of fine-grained ingenuity that solves real problems for actual workloads today, and therefore really important. Thierry works for NVIDIA. NVIDIA is specifically interested in sparsity, according to the chief science officer. So Thierry's working on that with adaptive float. He spoke about that. He spoke about the, eDRAM, which is embedded DRAM, taking advantage of less transistors, so less power to store something, but then it needs to be refreshed more often. But if you have transient data, you actually have the luxury of still doing that if you adjust the algorithm accordingly. And lastly, I want to mention the DVFS and the early exit ideas. In my opinion, also very interesting concepts that allow for more flexible, deep neural nets that can be adjusted based on the needs of the data that comes in. Thank you.